Hello, can people hear me? Okay, good. So I guess we'll make a start on this session. So this is the differentiable programming session, the first one. So there's going to be a session today and then another session at the same time tomorrow. So welcome. Before I sort of motivate what it is we're going to do today, we're going to do a quick bit of setup because won't take you very much time, but it might take a while to spin up. So I've put the repository name in the Slack channel, but you can also find it. I mean, it's kind of a long title, so apologies for that. But under the Cambridge ICCS GitHub organization, if you just put differentiable-programming-summer-school-2025. So it's a lot of typing, but it's quite easy words. You will find the repository. So I'll give a minute for people to get there. And as I said, the link is also in Slack. And then once you get there, we're going to open a code space. So if we click the green code button, instead of cloning locally like you would see on the left, we just click code spaces. And then I've already got one open because I've preloaded it, but you should see here, create code space on main. That's a big green button. So if you do that, then it will start spinning up. And basically, it will put you into a VS Code session in the browser that's running on GitHub Cloud, I guess. And so for those of you that aren't familiar with VS Code, you will have the file explorer on the left. This is basically just the file explorer for the repository, plus a couple of extra things we've added in. You've got a terminal at the bottom, which will put you at the root level. So if you put ls, then you'll see the root level of the directory. And by default, it'll also open the README. It won't be particularly readable because it doesn't actually render it, but you can read the README on the repository. So hopefully everyone's happy with that. But please, so this course was developed by myself and Niccolo, who's sat at the front here. So if there's any problems, just raise your hand and Niccolo will come and help out. And if there's more than one person, then hopefully other RSCs can help out as well. So yeah, is anyone got any questions so far about code spaces? Good. Okay, so in our experience, it might take 10 minutes for the code space to spin up. So if you just set it going, and then we can sort of go through the motivation while we wait. So the way it's going to work is we've got there's session 1 and session 2, you can see here. Obviously, we're doing session 1 right now. So if you click on that, you'll see there's some exercises. There's some images just for the notebook, and then there's this notebook, Jupyter Notebook. So if you click that, then I think maybe double click it actually, then it will stay open. You'll be able to view it in the VS Code session here. So I will reduce a bit of that. I think that's probably enough terminal room at the bottom. We'll stay in the notebook as much as possible, but there will be a little bit of jumping around because it's not all Python. But is that readable for people? A little bit more? Does anybody know how to zoom in VS Code?
Yeah, sweep your big spot. That sounds very interesting.
That's not working on this browser one. There we go, yeah, Control plus. It's 110% okay or further. Yeah, okay, cool. Yeah, so sorry, I'm a Vim user, so if I start typing Vim in the terminal at the bottom, then shout at me, because I tried using VS Code at one point, and I was doing that so much that I thought this just can't go on. Okay, so there's a few, sort of cells at the top that you want to execute just to pick up a few things, some modules, and you'll see that there's Python environments. Oh, actually, no, sorry, don't do this yet. There's one more step. There's one more step. We've got to source an install file. So you see there's this install script here. We want to source that. So that will also take a short amount of time. It's just going to create a Python virtual environment that you can run in. It's going to pip install various things that we can use. That looks like it might have had an error. Having a numpy, what? So it's created this virtual environment dpvenv. This did not happen when we tested it. We've installed numpy. Yeah, Nicola says he will look into it, but hopefully that's sufficient. So if we just make sure that we've got the things at the top of the notebook installed, then we should be fine. So that's npl tools, matplotlib, numpy, and pandas. Sorry about that. And then once that's done, it will have installed various things, and it will have also installed an automatic differentiation tool, which we'll come to later. So apologies that that wasn't very clear, but if you run the install script, you need to make sure that you type source install. And the reason for that is that it puts things into the environment. So if you look at the instructions on the repository, this is how you do it. If you just put /install, then that's not sufficient. So is that okay? Any questions? So yeah, you'll just need to, unfortunately, we'll need to run this source install and then also pip install numpy and pip install pandas, I think it was. And then once you're ready, we try to execute the first cell, and it will ask you what kernel you want to use for the Jupyter Notebook. And when I say we run the cell, you do Shift and Enter, for those of you that have not used a Jupyter Notebook before. So you click on the cell, Shift and Enter, and then you select the Python environment, and you'll see that there's this dpvenv, which is the differentiable programming virtual environment that we've just created. So if you click that, then it will use that Python for the Jupyter Notebook. It just means that it has the right access to the right modules. So you'll see down here it's doing some installing. And then when you get a tick, that means that it's passed. So we can then run the other cells. It can now import those modules because I made sure they're installed. And then there's just a helper function here. So in the interest of time, I'm just going to sort of carry on with the motivation. But if you're having any problems, then please do put your hand up. Okay, so differentiable programming. This is an enabling technology. So given scientific code to compute some quantity, it could be lots of different things, but a lot of the time we have scientific codes that computes a quantity. Differentiable programming allows us to generate derivatives of the quantities involved in the computation without needing to do any hand derivation or hand coding. So you're just writing the code for the primal, as we call it, just like the sort of standard piece of code that you want to run. And if you want to get the gradient or the Hessian or some other derivatives of something in the code with respect to something else in the code, then you can use differentiable programming. And some motivating examples. So when you solve nonlinear systems, when you do numerical methods, you need the Jacobian of the system. So this is like a matrix of first derivatives, and you can use differentiable program for this. When you're doing optimization, so ODE constrained optimization, for example, PDE constrained optimization, you need to compute gradients, typically. When you do training of machine learning models, which is something we'll talk about a lot in the summer school, you need to do backpropagation, which we won't cover in today's session. We'll cover it tomorrow, but that's also an example of differentiable programming. In certain formulations of uncertainty quantification, you use Hessians. That's a matrix of second derivatives, which you can compute this way. And then finally, in data assimilation, which people might have heard of or be working on, which is common in weather forecasting, you need to solve adjoint problems, which are very related to all of this stuff. So hopefully that's motivated you that this technology is used or at least can be used in lots of different places. In all of these cases, people have historically written code that does some hand coding, but you can save yourself a lot of tedious effort by using automatic differentiation and make it less error prone as well. Because if you're hand deriving large expressions, then that can introduce errors, human errors. So as a bit of summary of what we're going to do today, we're going to get a brief history of automatic differentiation, which is another term for differentiable programming, which I'll use quite a lot. We will learn about the forward mode and the source transformation approach. So forward mode is it's kind of like a method by which you compute derivatives. There's two different ones in the literature mainly. We'll talk about that one today and a different one tomorrow. And then source transformation is the way that the tool actually works. So there's a tool that does automatic differentiation. It's called an AD tool. There's two different types, so we'll talk about one of them today, one tomorrow. So you're kind of getting an example of a mode today and an example of an approach, and the same will be true tomorrow. So we're going to try out the Tapenade tool, which is a source transformation tool, and apply it to some test problems. We're going to verify that the code that it generates is correct both manually and also using something called the Taylor test. And then finally, we'll learn about compressed and matrix-free approaches for sparse problems. So that's kind of moving on to like realistic case studies rather than just toy problems. If you've got any questions at any point, please feel free to put your hand up and we can discuss them as they come up. That's fine by me. So with these sort of markdown cells, you can also click through those if you want to. It's the same, it's just shift and enter and it'll just move you to the next one. So it's preparation. So the terminology, as I've already said, we call it differentiable programming, but it's also known as automatic differentiation or algorithmic differentiation. There are subtle differences, but I'm just going to use them all exchangeably in this course. And AD is the term that we use most often for automatic differentiation. And just a bit of stuff on notation. So for some of us, including myself, it's been a little while since doing sort of school maths and that kind of thing. So we might want to refresh the notation for some of these concepts. So if you've got a differentiable mathematical function, so this isn't a code function now, this is a mathematical function f. So it maps from a space A into the real numbers, where A is just a subset of the real numbers. It could be the entire real number line. Then we denote the derivative of f with respect to x either as this f prime x, the Lagrange notation, or with the Leibniz notation, which is df by dx. They're used interchangeably, and hopefully you're familiar with both of them. Unfortunately, this didn't render, so sorry for that. But if you see an x with a dot above it, or any variable with a dot above it, be cautious, because it does sometimes mean derivative, it sometimes means something else, and that will hopefully become clearer later. But if you're a physicist, then, and if you see x dot, don't immediately think it's a derivative. So we'll come to that, hopefully it'll become clear. If you've got vector functions, then it's very similar. We've just got a bold font is what we're using here. Bold just means vector. And then if you've got a vector function with multiple inputs, then you need to start thinking about, well, sorry, any function with multiple inputs, you need to start thinking about partial derivatives. So hopefully people are familiar with partial derivatives. If we compute the partial derivative of the first of a function with respect to its first argument like this, and then the gradient is when you put them all together. So hopefully this notation is all familiar to people. We have a similar thing for if it's a vector function, but then this will now be a matrix rather than a vector. And then when it comes to derivatives in code, you'll see this underscore d notation. So it'll be like f is the function, and it'll be f underscore d is the derivative of f. And so d, you can either think of it standing as for derivative, or like I was saying a minute ago, it could also stand for dot. It's kind of both at the same time. And this is quite standard in the AD literature. So a bit of history. Believe it or not, automatic differentiation has its origins in the 1950s. So it's been around for a very, very long time, and it's gone in and out of fashion many times. It's enjoying quite a fashionable moment, but it has sort of ebbed and flowed over the years. It found a wider audience in the 1980s, and that was largely thanks to the modern programming languages and computer power. So Wenger discovered the forward mode, which is discovered or invented, as we could have a philosophical discussion there, in 1964. But this was before sort of the modern programming languages existed enough to handle this. So he had this idea of what it was and how it could work, but had no way to implement it, which is kind of interesting. So it was thought up in the 1950s. It didn't get implemented until the 80s, and then it was developed quite a lot by Grievank and others in the 1980s as well. So I've just included a snippet here of Wengert's paper in 1964, a simple automatic derivative evaluation program. But as I said, there's no numerical experiments in this paper. It's just a sketch. So what's the idea? Well, the idea, again, we're going to go back to a bit of A-level maths on the chain rule. So effectively, what the automatic differentiation is under the hood is just a lot of applications of the chain rule. So you have a program that has lots and lots of operations inside it. We need to have the derivatives of each sort of operation and then a way to chain them all together. And the chain rule is the way that we do this. So if you've got two functions f and g, then mathematicians would use the notation h equals f circle g. Well, despite doing a maths degree, I've actually got this the wrong way around. So no, I haven't. I've got it the right way around. It's all good. Yeah, this is the right way around. So f circle g means you apply f first and then g, confusingly. So if h of x equals the composition of f and g, then that's the same as g of f of x. So hopefully people have seen that before, although we won't be using that composition notation too much. And if you have that composition, then the chain rule looks like this. So you take basically, to get the derivative of h, you have the derivative of f multiplied by the derivative of g evaluated at f, not evaluated at f prime. So you don't actually need to worry too much about this because we're not going to be doing any maths by hand, but this is just to give you an idea of what the computer's doing. And for those of you that are more familiar with Leibniz notation, you can also write it this way. So dh by dx is dg by df, df by dx, and then similarly for partial derivatives. So is there either any questions, or has anyone not got their code space up and running yet? Is it still loading for anyone?
I just sent a message with command to make up for the error we just did. We saw the package committed, so I just got the thread in the message that jumps in.
So everyone's got it running? Okay, there's no hands, so it seems like it's okay. Good. So we're going to start with a simple example. So we've got two functions f and g. F is a function of two variables. It's just, if you take f of x and y, then it's just a product. And then g is a function of a single variable. And if that's z, then it's just the first component is sine of z, and the second component is cos of z. So there's going to be some exercises, and there's going to be some optional exercises. So the optional ones, I will not go through in the session today, but if you want to have a go at them, then you can do that. And then there's the solutions here. I won't click on it because I don't want to spoil it for anyone, but if you click on this, then it will reveal the solution. So feel free to do that at your leisure. So we've got these two different functions, and the exercise is about showing that we can combine them together. Sorry, I've changed the notation here. Forget the x and y. This is what we will use going forward. I thought I'd change them all to this, but I've obviously missed one. So this is a slightly better notation. So we'll start again. F of x equals the first component of x times the second component of x. So x is a vector, right? With two entries. And then g of y is sine of y, cos of y. So these are the same functions. I'm just using different dummy variables for clarity. So hopefully that's not been too confusing, but we have those two functions and we can represent them with directed acyclic graphs, or DAGs. So for the first one, see if I can fit it both on. For f, we're mapping two inputs, so there's x1 and x2, and we're mapping them to a single output y by multiplication. And you can see that how do we get from x1 to y? Well, we multiply by x2. And how do we get from x2 to y? We multiply by x1. It's maybe a fairly trivial diagram, but it will become useful later. Sorry that all these equations have not rendered. That's quite annoying. And then similarly for the second one, how do we get from y to the two components of z? Well, for the first one, we take the sine, and for the second one, we take the cos. So hopefully that's fairly straightforward. And then when we compose them together, I've just sort of worked through the hand derivation here because we're going to verify, we use this to verify the AD tool later. But I mean, I'm not going to read it out because that would be painful, but you can read through it yourself and it will show you what the different derivatives are. So if we have df by dx1, then we get x2. If we get df by dx2, we get x1. And if we have dg by dy, then it's this thing, cos of y and minus sine of y. So hopefully this is all fine for people. And then we can do the chain rule as well, so that we find that dh, so h is the composition, the derivative of the first component of the composition with the first component of the input is this thing, x2 cos x1 x2. And then we can have similar expressions for these other things. So I won't spend too much time on this. It's just sort of showing that these are the answers we expect because we're going to verify them later. So yeah, don't get too hung up on those. So what is it that this AD tool actually does? In forward mode, which is what we're talking about today, it is all about directional derivatives. So for those of you who've done vector calculus, you will have heard of this. The idea is that you're taking a derivative in a particular direction. So this can be thought of as taking the Jacobian, which is where if you've got a vector function, then the gradient of that vector function is the Jacobian. That's just the name that we use for it. And its notation is this thing here, grad f. If x dot is a direction vector, then the Jacobian times x dot is a Jacobian vector product, and it's like having the derivative in that direction. And so we call this thing a seed vector. So this is where I was saying x dot can get a little bit confusing because here it's not necessarily a derivative, it's just a direction, but this is the notation people use in the literature. So seed vector is one of the inputs, which is saying what's the direction we want to compute the derivative in. So the JVP is the Jacobian vector product. We'll hear that term over and over again. And the JVP it depends on three things. We want to know the function that we're differentiating. We want to have the point in the domain space that we're evaluating it at. So you can see here that we're going to be evaluating f at x. So you need to specify what x is. So you're computing it for a particular point, not like for all possible inputs, because that's something else. That would be more symbolic differentiation, I guess. And then finally, you have this direction. So this is called JVP. That's what I'm going to call it throughout this course. But elsewhere in the literature, you might hear the tangent linear model, or TLM. That's also something that's commonly used elsewhere. So yeah, as I said, we can think about the seed vector as a direction. In many cases, it is a derivative from another part of code. So let's say you applying this AD to two different sections of code, and then you want to glue them together in order to compute the gradient for both of them. Then you need a way to sort of transfer that first gradient feed it into the gradient function for the second one. So in that case, this x dot would be a derivative. It would be the derivative of whatever's upstream. So we'll see more examples of that very shortly. And as far as this computation here goes, though, we can think of whatever that upstream calculation is as like passive. It's not, we don't actually care about it, it's just a number. Whereas what's going on in F is active. So when I say active, it's like we're going to differentiate this code, as opposed to passive, we're not going to. And this computation is matrix free, so we don't actually need to know what the Jacobian is. Like I was saying, we're not computing the Jacobian for all possible inputs, or even the Jacobian at x. What we're computing is the action of the Jacobian on a vector. So what is the derivative in that direction? So you could have computed grad f, but you don't need to. So to revisit these DAGs, so we saw before there was these two sections. So there was the orange section for f and the blue section for g. And if we have these seed vectors, the seed vector x dot, you can write it as x dot 1 and x dot 2. These sort of, in the derivative of the program, these feed in. And then as we go through the program, the idea is that as well as computing the function, we also compute the derivatives of this function. And we'll come back to this diagram later, but basically, because we're working with partial derivatives, the derivative going down here, the derivative of this operation is still going to be multiplying by x2, because x1, if you've got the partial derivative with respect to x1, then x2 is constant, because it's a different thing. And so you still have to scale by this x2. And similarly for the other branch, whereas for these ones here, we're going to have to differentiate through sine and cos. And then the output is z1 dot and z2 dot. So has anyone got any questions so far about this stuff? If not, then we'll move on to an example. Well, we'll talk about source transformation first, and then we've got an example that will hopefully make things a bit more concrete. So the high level idea of source transformation is to take the code for a function or subroutine or whatever you want to call it, some code anyway, and given that and given a seed vector, we want to generate the code for its derivative, which we call FD. So if f is a function of x, then FD is a function of x and x dot, or xd, because that's the seed vector. So we're generating the code for the directional derivative, and with a source transformation tool, you'll take the code for the input as a file, and you'll spit out another file for the derivative. The approach we'll see tomorrow is different. So this is a static analysis tool, like we heard about yesterday. It's done ahead of time, so it's not at runtime, is what that means. It's even actually pre-compile time as well. Often the difficult part about working with source transformation is stitching this into your build system. So like you've got this model that does loads of stuff, and then all of a sudden you've got gradients for bits of the code as well. So you need to figure out where they fit into the build system for the model. It's not necessarily a hard problem, but it's something you have to think about. And the other thing to note about source transformation is that unlike the approach we'll hear about tomorrow, source transformation has very, very few tools. And the reason for that is it's very hard to implement this kind of thing, because you've got to pass through code, you've got to do transformations on it, and then you've got to be able to write it out again. So Tapenade is the sort of the best known one in the field. It's been around for some decades, and it supports differentiation of C, Fortran, and then there's experimental support of Julia. OpenAD was also around for a similar amount of time, but it's unfortunately no longer maintained. TAF is another example, which is for Fortran, but it's commercial. And then Cyad is related to Cyclone, if anyone is aware of what that is. That's also a work in progress, but that's for sort of domain-specific codes for weather modeling. So we're going to work with Tapenade because it's out of these ones that I'm aware of, it's definitely the best one to use. So if we go to the source F&G example source transformation, we're going to work with those functions that we saw, and we're going to do automatic differentiation. So I'm aware that some of you don't know Fortran, and there's going to be Fortran in this course, but I will keep it hopefully fairly simple. So I was saying to a few people yesterday that Fortran is quite readable, so hopefully my Fortran will be readable. So we've got a subroutine, which you can kind of think of like as a void function. So x is f of x and y, but here y is actually an output. So x is an input, y is an output, and that's denoted in Fortran in this way. So intent in, so input, intent out, y. So these are both real numbers, and one of them is a vector, dimension 2. So hopefully that is all clear. And y equals the product, which is what we saw further up. And similarly for the G subroutine, we've got one input, which is y, and we've got a vector output, which is z, and z is computed in this way. So there's an exercise which we'll give a few minutes for. There's four parts, and 2 of them are optional, so we won't go through those ones, but we will run through exercises 1 and 2. The solutions are all shown below, but please give a go before you open the solutions. So the first one is if everything's gone well, then down in the terminal, you should have tapenade in your path. So if you put which tapenade, then it finds you the binary, and you can run tapenade and then some commands. So if you start out with tapenade -h, it'll give you a lot of options, which I don't expect you to understand all of, but it will be useful for us later. And then the second one is to apply the tapenade tool to these two subroutines. So you've got f.f90, g.f90, and if you apply tapenade, then you will get these derivatives. And I think if you just type tapenade and then the file name, it will probably work. But if you want to do things properly, you can specify, you can use the -head argument, and then sorry, this should be in quotes. In quotes, you would then put something here. So the name of the procedure that you want to differentiate. So it's a subroutine name. So that's either f or g. And then what are the dependent variables? So it's either x or y. And then what are the independent variables? It's either y or z. So we'll give a few minutes, and please put your hand up if you've got a question. Yes.
Just one question. Where do you put the file name stuff? Is it all the head part or at the end?
At the end, yeah. Yeah, so if we, in the terminal here, so as I pointed out, there's session 1 and then exercises and then FG. So if we go session 1, exercises, FG, then you will see that there's f.f90 and g.f90 and then a makefile, which we probably won't use. So if you navigate to that location, you'll be able to do some stuff. So, I mean, I might as well just go through the first one now. All you got to do is type tapenade -h, and it will spit out a lot of help. And so it mentions this head thing, but unfortunately doesn't give you very much information. Yeah, so if anyone has finished the exercise, then if you look at exercise number 4, the optional one, then you'll see a bit of information on how this kind of works, how the AD tool works. Yeah. Okay, I think in the interest of time, we'll carry on. But if you have any more questions, please just put your hand up, and Nicola will come over. So I'll run through the solution to exercise 2. So we're in this location in the FG exercise, and as we say in the hint, you can type tapenade, and then you can type, well, I didn't mention this actually, but you can put D if you want, or tangent. Either of those means forward mode. So it's not compulsory, but you can do that. It will just do it by default. And then you can put head and then some quotes. And in the quotes, we've got the procedure name, then the dependent variables, and then the independent variables. So the procedure name for the first one is F. And then in brackets, we have the dependent variables, which is just X. And then we have a slash. And then we have oh, sorry, wrong way around, sorry. Y, and then a slash, and then X. So in this case, X is the independent variable because it's the input. Y is the dependent variable because it's the output. And you've got to obviously give it a file. Is this the wrong way around? There, okay, so someone else asked about this. There's this slash here. I can never remember which way around it is. So if you just flip it to be the opposite slash, then it should work. Alternatively, you can reorder things. So if you use the backslash, but put X and then Y, then that will still work. So it's just a very confusing notation. Either you do, so this is actually wrong, so I do apologize. That should be backslash. So you either have it this way, so dependent variables slash independent variables, or you flip it and you also flip the slash. So hopefully that didn't trip too many people up. but we've generated the f underscore d dot f90. That's the derivative, and we can open that, and you see we've got this nice auto-generated code. It's got some header from Tapenade, and the reason I asked you to specifically type out this head stuff is you're basically telling Tapenade what the dependent and independent variables are, and so it can put useful information in the doc string. What also works is if you just type Tapenade, you might have noticed this, Tapenade f, then it will just generate, double click it, I guess. Oh, that does look the same. Interesting. Well, anyway, that will also work, but I find that it's good practice to be more specific in what you're differentiating, because in some cases you've got lots of inputs or lots of outputs, and you don't necessarily want derivatives with respect to everything. It can get very, very messy. And if we look at the code, we'll see that it does actually evaluate f still. So x and y are still inputs, and we still compute y equals the product. So forward mode is computed eagerly. And so the idea is that you can just replace your call to f with a call to f underscore d, and it will still compute the function you want it to compute, but it will also compute its derivative. And so for that, we have an additional input, which is the seed, and we have an additional output, which is the derivative. So we've got x dot and y dot, and then the product, sorry, the derivative of the product is this is like the product rule, which you might remember from sort of A-level maths. And then if we do the same thing for G, then you will have seen that you've got some other derivative code where we've now got derivative. Initially, there's a sign in the first component and a cos in the second one, and then that's changed because of the way that the derivatives work. So hopefully everyone's happy with that. And we'll move on to the next section. So this is, we're going to revisit the F and G example, but we're going to take a look at the Taylor test. So again, we're going to go back to some A-level maths. So hopefully people are familiar with the Taylor expansion. So for a function f evaluated at a point x in its domain, you can add on a small perturbation, epsilon, and then compute this Taylor expansion. So this is assuming that f is infinitely differentiable, which isn't necessarily true, but let's just pretend it is. And it will be for our examples. You have this expression where you have f of x, f of x plus epsilon is f of x plus this first derivative term that's multiplied by epsilon, and then you get these higher order terms that are multiplied by epsilon to the power of n, and then they also have a divisor. But the important thing is if we sort of take this as an approximation just to the second order, or first order, sorry, then we basically have f of x plus epsilon is equal to f of x plus epsilon times the derivative of f evaluated at x, and then everything else is sort of quadratic term and above. So if we're happy with that level of error, then that's a reasonable approximation, and that's how we get the forward difference operator that people will be familiar with if they've done finite differences. And so basically all the Taylor test is checking that forward differences of this flavor converge towards what you expect the gradient to be. So we know it's well established that supposing that this function is infinitely differentiable, this will converge, this forward difference here will converge towards the true gradient. And if it converges towards whatever we've got, that means whatever we've got is the true gradient. Hopefully that makes sense. So here, f underscore d is the AD generated result. And for the sake of this one, I've actually just translated the functions into Python using NumPy. And so you'll see that there's a few cells here that implement this Taylor test. So we've got f, which again is just written out as a product, g, which is this sine and cos term. You can run that cell, And then this is just translation into Python of the derivatives that we've just computed. So we've got f of d, f underscore d, and g underscore d. And we've got this Taylor test code, which I'll lead you to read through in a bit more detail. But effectively, we've got an arbitrary input, x. So I've just chosen 1, 1. A seed vector 1, 0, which we'll come back to in a sec. And then we do this loop where we take several different finite difference approximations and we check that they converge. So if we run that cell, then you'll see this plot. So what that's saying is that as this spacing is decreased, so it's actually going from right to left, you take a large spacing of 1, and then as you reduce this perturbation or spacing, the convergence rate is quadratic, which is what we expect. So there's a small exercise after that, which is optional, which is for you to go back and to compute the derivative with respect to x2. So why is this the derivative with respect to x1? Does anybody know? So just glancing at this code, the important parts are in the top few lines. Why is this derivative code here giving you the derivative with respect to x1? Yes? Exactly, yeah. The seed vector is 1, 0, and so the direction is just in the first direction, and it's not in the other one. And so hopefully that's a hint for how you do the optional exercise. Okay, so we're now going to look at a sort of more involved example, and we're going to be looking at ODE constrained optimization. So unfortunately, there's like several references to derivatives here. So we're solving. There's now ordinary differential equation where we're solving this equation that's 1D for, no, it's not 1D, sorry, 0D because it's an ODE. Du by dt equals a function of u for some initial condition. And sorry, no, it's a function of time. U is a function of time, and so we've just got this du by dt. There's no other partial derivatives going on there. And we're going to consider the simple case of just du by dt equals u. And the initial condition that at 0 is 1. Just looking at that, does anybody happen to know the analytical solution? Oh, someone says it's unstable. Okay. Well, the analytical solution for that is just the exponential.
Physically unknown.
Sure.
Nonsense.
Physically nonsense. Yeah. Apologies.
Minus.
Okay. Yeah. Sorry that I've chosen one that's physically nonsense, but
No, I mean it's mathematical, but
yes.
physically.
Yeah. Sorry, I was initially a mathematician, so maybe that's why I went for this. So yeah, we've got this one that will not be useful for your studies in the Earth, but we've got the analytical solution is the exponential. So the property of the exponential is that when you take the gradient, it's the same thing. So we're gonna. I've already done the optimal exercise for you, but we're going to solve this problem using different methods. So hopefully you're familiar with time stepping methods. So we've got forward Euler and backward Euler are kind of like the simplest cases of this. So we're kind of coming back to the central differences. The forward differences in a sense. So it's a similar concept here. It's an approximation of the time derivative here. So we've got du by dt is being approximated in this way, where if you have successive time steps that are indexed by k, then at the kth time step, we have the explicit Euler method computes uk based off this formula here that involves uk minus 1. And then for backward Euler, it's very similar, but now we have f of uk. So you have to solve a nonlinear system in order to get what the solution of uk is here, because you can't just sort of rearrange it simply. As it turns out for us, we can, because f of uk is just uk. But hopefully people are already very familiar with this kind of thing. But we're going to look at the theta method, which is where a way of combining these is kind of like a homotopy method where you introduce a parameter theta such that theta is anywhere between 0 and 1. And if it's 0, then you recover explicit Euler. And if it's 1, then you recover implicit Euler. Or sorry, forward and backward, I should have said, because that's the words we're using here. Now, that's the theta method. And if we apply it to our problem, then you can actually, as I just said, you don't need to do too much. You don't need to solve any nonlinear systems per se. You can just do it by hand. And you have u of k equals this update. So you take whatever you've already got and you scale it by this ratio here involving both the time step and also the parameter theta. And we've got some more Fortran, so that's exciting. If we now navigate to the ODE example, so you want to go back one level and then into ODE, then you'll see that there's some Fortran source code there, and there's a makefile as well, which we'll be using. So you can take a look through sorry, it should be theta method mod there rather than theta methods.f90. But when you look inside there, you'll see various bits of code, including the code for this theta step that we just looked at, and also the code for the actual theta method itself and for the initial condition. So I'll leave you to sort of play around and have a look at that yourself. And then we also have code for the forward Euler method and the backward Euler method, because they're just special cases 0 and 1. And you can see here for the forward Euler one, we just choose theta equals 0. And then we pass that to the theta method. So there's a little bit more Fortran syntax than what we've seen before. When you want to execute something, like before we just had these subroutines and never used them. When you want to execute something, you need to have a program. So this is going to be the forward Euler program that gets run. We're using something from a module, so you can think of this like an import, like you would have in Python. You need to import the theta method from the theta method module. Implicit non, you can ask someone later. Then here we have some parameters. So theta equals 0, u is going to be the solution, and then we've got the name of a file that's getting passed into this theta method. So hopefully it's not too confusing. It's a simple program that's going to run this theta method for a particular value. And so there's some details there on how to run this code. We've provided some make files that will hopefully make it quite straightforward. So you can just run make forward Euler, and it will there'll be some compilation that's just done behind the scenes there. And then you can also do make backward Euler. And then the way that we run these is just sort of as an executable, so dot slash forward Euler and dot slash backward Euler, so that it won't print anything. But you will then hopefully see that when you do ls, you've got various things. So there's these module files. Down the bottom. So you've got these module files and these .o files. This, for those of you that aren't familiar with compiled languages, these are the kind of things that come out of the compiler. So don't worry about them too much, but that's what's used to sort of link these different things together. There's this backward Euler and the forward Euler things in green. They're the executables for the program. So we take the source code and turn it into these executables. And then when we run them, it produces some CSV files, which is sort of keeping a track of what happened during the simulation. And then coming back to the notebook, you can read these CSV files in and print and plot them. So you'll see here that we've got the analytical solution plotted in black. So that's the exponential, just u equals e to the power of t. So that's what we want to get with our numerical method. And with forward Euler, it's consistently underestimating this. And with backward Euler, it's consistently overestimating this. So hopefully this is familiar from numerics courses. And the motivation here is that for using AD, it's like, well, we've got these two different approaches where theta is 0, theta is 1. Well, how do we figure out the optimal value of theta such that we get a good match with the analytical solution? And the way we're going to do that is using AD. So we're going to use a gradient-based optimization method called gradient descent, which I'm sure people will have heard of. And it allows us to solve this minimization problem where we minimize some cost function in the space theta between 0 and 1. So we can't have theta less than 0 or greater than 1 because it doesn't make sense. But within that range, we can do an optimization such that a cost function is minimized, where the cost function is basically the error. So because we know the analytical solution, we can compute the actual error. I mean, in real applications, you wouldn't know the analytical solution, but for this sort of idealized problem, we do. And so we can do this optimization. And for those of you that are more sort of on the numeric side of things, the forward Euler and the backward Euler methods are first order accurate, which is what we saw before. The error term is quadratic. And then by optimizing the theta parameter, we can actually get a second order accurate method. So that's the motivation here, is that we take the same framework and we can improve it by tweaking theta. So the exercise is to navigate to this directory and apply the forward mode of AD to the theta method subroutine by differentiating this module with Tapenade. So we'll give a few minutes for that. I think it might be sufficient to just type Tapenade and then the file name. But if not, then take a look at the solutions and you can be more specific. But the downside is that Tapenade needs a bit of extra information in order to handle these modules. So yeah, we'll leave a few minutes for people to play around with that. And then if you find that you've finished that, then feel free to go on to the next step here, which is where we do the gradient descent. So we're going to be choosing this cost function. As I said, it's just the square of the error between the analytical solution and what the numerical solution. So we're going to need to also differentiate this cost function code, which is in a separate file. And then we're going to need to run the gradient optimization. I guess in the interest of time, maybe we just combine these exercises together. So yeah, the first one is differentiate the theta method. And then we've got these down here. So differentiate the cost function and check that you're happy with it. And then run the gradient descent optimization algorithm and visualize results. And then finally, there's an experiment. If people find that they finished, then they can play around with different tolerance values to see if that affects the convergence. Any questions before we start work on that? Okay. So I'll just go through the first bit here. So it seems like some people have gone past this already. So the first section is just to differentiate the theta method mod. And I think even though there's a few things defined in there, it should be sufficient to just put Tapenade and then theta method mod.f90. So it will automatically detect what are dependent variables. And if we look at that module, oh, I'm in the wrong place here. If we look at that module, I think part of the way that it does this is that there's only one of these subroutines is declared as public. So this is starting to get into slightly more advanced Fortran. So I won't necessarily dwell on it too much, but it's figuring out that theta method is the thing that it needs to differentiate with respect to. And I guess that's also because the theta method subroutine is calling the other subroutines. And so we're going to get the derivative of u with respect to theta. And so when we open that, a bit more space, we've got this thing here. So it's going to have the code for various different things in here. But you'll see that there's the subroutine for the initial condition, which is just the same as it was. There's the derivative of the theta step method. There's the original theta step method. And then there's the derivative of the theta method and then the original one. I just realized this. We tried to set up Fortran syntax highlighting, for this, but it didn't seem to work. I wonder. Yeah, I wonder if you can just type Fortran and then install. I think it's this one. Just for those of you that. There we go. Yeah, so then you get some syntax highlighting. Sorry that we didn't manage to get that set up automatically, but I might make it slightly more readable. So as you go through this file, the red is sort of the keywords. So you see that there's this one subroutine and then others and comments are in gray. So hopefully that's slightly easier. So yeah, if you just click extensions and then search for Fortran, it's the modern Fortran one. I think the other one does work, but modern Fortran seems to be better, I would say. So in the second part, oh no, sorry, I don't think I finished. No, I did finish this. So that you can see the solution here. And this is what I was saying about needing to be more specific when you differentiate something with modules. So because they live inside the theta method mod, you need to put, similar to how you would in Python, you need to tell it which module this thing lives in. So you've got theta method mod dot theta method. It's just the way that you specify the name. And then there's also this thing here, target tangent module name, and this just customizes the suffix that you get. So when we look at this here, it's actually not going to work with the other code. So you see it says theta method mod diff. Strangely, it will by default always put diff when you have modules. So what you need to do instead is to specify what this extension is. So instead of diff, just put _d. And so when we go back here, we can see if we put Tapenade tangent module name _d. Sorry, that percent sign is also wrong. Theta method mod dot theta method theta u. And then you need to pass the name, and it does the derivative there. So when we reopen that, we should get here. So now it's theta method mod d rather than diff. So yeah, apologies again. This is because it's been copied and pasted from something else. That percent sign is not meant to be there. Any questions on the exercise so far? Okay, so we'll go on to the second part. So in the second part, we have the derivative of the cost function. So we can do a very similar thing where we're now got a cost function, which is also in a module. You can put cost mod, and then within the module, you've got cost function, I think it's called. And then the inputs and the outputs, let's check what they are. So when we click on cost mod, we see that U is the input, J is the output. And so we go U and then J. And then we get its derivative, which is here. So as you can see, as before, we've got this, it's computed eagerly. So J equals U minus E squared, which is just the original evaluation of the function. And I should mention, I've not mentioned this before, but Fortran doesn't care about case, which is why it does strange things with case. So a lot of things go lowercase, a lot of things go uppercase. Like in Fortran, none of it matters. So that's why it's done that. But then you also get the derivative here. So when you have a square, you take the derivative by putting the 2 in, you bring the power in front, and then there's also the scaling by the derivative. So we've still got U minus E. The power is now in front, and then you're multiplying by the derivative. So it's doing exactly the same thing as you would get with chain rule. And then the second part is to run the gradient descent algorithm. So this will you will have needed to get the name of the module right in the other bit for this to work. And if you type make gradient descent, what's gone wrong here? Oh, I was about to use Vim. Nicola, do you have any idea what's gone wrong here?
We can try.
Right, now it works, whatever. Yeah.
Yeah.
Thanks. So hopefully people managed to compile that fine. And then if you run gradient descent, you should see that it's converged in 755 iterations. Given that we're all using exactly the same Linux setup, we'll probably all get the same answer, I would have thought, unless anyone's doing this locally. This is a very simple gradient descent algorithm with a fixed step length. So there's quite a lot of iterations. What did people find out? Did people have a chance to do the playing around here? So play around with the optimization parameters. Did anyone find anything interesting? Did anyone get to that part of the exercise? Yeah, some people. Okay. Well, you can go back to the gradient descent thing here. So we can see that there's some optimization parameters that get set. So maximum number of iterations, gradient tolerance, divergence tolerance, alpha, which is the step length. So as I was saying, it's just a fixed number. And what we mention here, playing around with the optimization parameters, you find that if you increase this value, then you can actually get convergence faster. So if we increase that to 1.5, say, because Fortran's compiled language, you'll have to rebuild. So you put make gradient descent, and then you run it. So before it was 755 iterations, and now it's 503. And you can keep increasing this. I think that one still works. If you put 0.199, it'll converge in 378 iterations. If you put it any larger than that, it does start to break. So this isn't completely robust. It's a very simple implementation, but there's potentially some more optimization that could be done there. Yes. Yes. Yeah.
Variables.
Yes.
How do you use this? How can we apply that?
Yes.
Let's we use. I'm doing those. Like the technical part. I think I can reproduce it, but then I don't know how it would apply this into my instance.
Yes, that's a good question. So the question was, how do we actually use this thing in research? So hopefully there will be a bit of a motivation of this later in the session at the end. There will also be a lot more of that in tomorrow's session because we kind of need to get through the basics of automatic differentiation before we can start to apply it to things. So applying this tool, one of the simplest things you can do is sensitivity analysis. So if you can compute the gradient of an output with respect to an input, then you can conduct experiments on like, if you have a perturbation in that particular parameter, how does it affect the model? And then, yeah, there's other more advanced things like uncertainty quantification, stuff like that you can do. Yeah, we won't actually see a real application in this notebook, unfortunately. But if you look in tomorrow, if you ever come to tomorrow's course or you watch the recording or look through that notebook, then you'll see some stuff that's hopefully a bit more relevant. Yes.
So we were using gradient descent to work out the optimal beta value.
Yes.
How do we actually see what that beta value was? Like, where is it output?
So I think it's actually the next cell. So in the next cell, we'll have a look at the optimization progress. So that's like what you see, when you do machine learning training, is just optimization basically. So you'll see these, when you do that, you see these kind of loss curves, that kind of thing. The cost function is just like a loss function. And then the cell after that, sorry, yeah, we should have come up to here really before we moved on to the next bit. You'll see the optimized value is just whatever theta ended up being. And In this case, it's just shy of 0.5. So for this particular case, you can see that if you have theta is 0, theta is 1, then it's not very good. But if you have theta is 0.5, well, just under, then it has a very good match. So this is just, the cost function here is that the values are the same at the end time, but we could use a more advanced cost function if we wanted to. So yeah, as we might hope, theta optimized gives a better approximation. So there's not a whole lot of time left, but hopefully we can just go through this last example, which starts to come a little bit closer towards how you would use it in research, because obviously they've all been very toy problems so far. So we've got this JVP, the Jacobian vector product. Question for the audience, how can we use this to compute the full Jacobian? So given a seed vector, we can compute the JVP. How can we compute the full Jacobian? Any ideas? Yep. So you choose the seed vectors for each of the canonical. The sort of simplest thing you can do is to take the canonical unit vectors, and by which I just mean the columns of an identity matrix. So the first one is 1, lots of zeros. Second one is 0, 1, lots of zeros. And the last one is all zeros and then 1. Then you can use this formula here to show that if you just do this JVP as many times as there are unit vectors, then you can recover the full Jacobian. And this is actually called vector mode. So whilst we could go through our code and apply this JVP several times with Tapenade, it's generally more efficient to just have a single call that will do that under the hood, because there's some optimizations that it can do. So what we call the VJP is the vector Jacobian product. And with that one, we've effectively got a seed matrix now. So the seed matrix is that when you take all the seed vectors and you squash them all together, you've got this capital X dot seed matrix. So the VJP is defined in this way. And so this is, maybe starting to get a little bit more relevant. So if we think about a classic central difference approximation that you would use in finite differences, again, this is another sort of tangential reference to derivatives that we're not computing d squared u by dt here, or dx here. This is just a quantity that when you use this finite difference stencil, the matrix that comes out of it is the thing that we want to compute. So the Jacobian of this stencil, basically. So this is very similar to what we saw before with the forward differences. This is a central difference now for the second derivative. And if we have a grid of points, so this is now spatial rather than time, then the central difference approximation looks something like this. So the stencil at point xk is evaluated in this way, where h squared is the space in between the grid points. So hopefully people are familiar with that. And there's this central diff mod that implements it. In the special case that we've got periodic boundaries, just for simplicity, it means you don't have to worry about edge cases. But for the interior points, this is just the stencil that we saw above. So the point to the left minus 2 times the point plus the point to the right, divided by h squared. And then these two are the special cases for periodic boundaries. And we have a program that computes the dense Jacobian, and that'll become a little bit clearer what dense means in a second. But this is going to use exactly the method that we just described, where you apply the Jacobian vector product to each of the seed vectors. And so there's a couple of details that I'll leave you to read at your leisure. But basically, we have this program here, which has some various parameters. So there's 10 grid points. So we've just got a grid in 1D with 10 points. We've got a uniform spacing of 1. U is the input vector here. The approx is the stencil that we're computing for the finite difference. We've got the seed matrix now for the VJP. So that's got m different columns. And then there's the full Jacobian that we want to compute. So you should be able to run this thing. You'll see that it sets up some arbitrary input, which is just u equals 1 everywhere. And I'll leave it as an exercise to the reader to check that it's fine to do that. there's a seed matrix, which is just initially it's 0, and then we put 1s on all the diagonals. So this is a identity matrix. And then we pass it to this, the vector mode of Tapenade. So we'll generate this in a second, and then we can write it out to the file. So I think we've skipped a step here somehow. Yeah, sorry, I missed the exercise. Apologies. So the exercise first is to apply Tapenade in vector mode, which will allow you to get this central diff underscore dv. So the v here is vector. So we're getting, instead of underscore d, it's underscore dv. And we'll give a minute or two just to do that. So you should be able to do something very similar to what you've done already. You just need to figure out how to run in vector mode. So just as a reminder, if you put tapenade -h, then that'll give you the help. Unfortunately, tapenade -help doesn't do anything. Hopefully people figured out that it's as simple as just passing dash vector. So you can see here that in order to generate this derivative, we put tapenade, and then, sorry, again, it's got this % sign that's just it's crept in there. We'll make sure that those aren't there in tomorrow's session. So if we open that back up, you should find that it's tapenade tgt module name, where tgt is tangent, and you put underscore d, and then we type head, and then this central diff approx, and then u. So we're computing the derivative of the approximation with respect to u, and then we have this vector. You need to be able to put it in vector mode. Central diff mod. I just realized I'm in the wrong location, so that's not going to do anything. But if I go into the sparse directory now, which is the one we're working in, then you should be able to run that. And when we look at the output, we have central diff mod dv, so the vector derivative, and you'll see that there's an input u and also an input ud, so that's the seed vector, and then an output approx and an output approx d, which is the derivative. And again, it's a bit messy now because there's these different cases, but hopefully if you work through this code that's generated, you can convince yourself that you're happy with it. And at the bottom there, you can just see the function itself being evaluated. And then going back to the notebook, as I said before, when I jumped ahead, you can build this dense Jacobian thing. Hopefully people have figured out that it's just like the other examples. We just type make dense Jacobian, and then we can type /dense Jacobian, and that will run it. And what that will do is save a file which we can now view in the Jupyter Notebook. So for those of you that are familiar with finite difference methods, this is kind of the classic tridiagonal matrix, and it's the one that we've chosen for this example. So you can see it's all -2s on the diagonal, all 1s on the off diagonals, and then because we've got a periodic, it's like a periodic domain, we've got 1s in the corners as well. And this is very clearly a sparse matrix. There's lots of zeros in there. And so as soon as you see sparse matrix, you should be thinking, well, how do we make this more efficient? Because surely there's some compression that can be done. And so when you have this, when we compute this full Jacobian here, what happens, we compute it by just taking all of the canonical unit vectors. But what about when n gets very large? And what about when the Jacobian is a sparse, as I've just said? Like if we've got a 1,000,000 by 1,000,000 matrix, we're going to need to do 1,000,000 JVPs, which starts to become extremely expensive. So firstly, you start to question, well, do I even need this full Jacobian anyway? Can I not just do a matrix-free JVP application? And then the other question is, well, if I really do need the Jacobian, then how can I do it more efficiently? And as a motivating example, this is the simplest possible case of a sparse matrix. Well, I suppose the zero matrix maybe is the simplest possible case, but one of the other very simple cases is a diagonal matrix. So if the Jacobian of f at x is diagonal, then it looks like this, where j1 and all the way to jn are just some numbers, and it's 0 everywhere else. then for some seed vector, the JVP looks like this, where you just have J1 times the seed entries. So this Jacobian matrix, diagonal matrix multiplied by this seed vector gives you this. Now, if we make the clever choice of seed vector of just all ones, which is commonly denoted as E, confusingly, then with a single Jacobian vector product here, so we've got, this is like an AD tool that's computing the JVP applied to the seed vector E, and then it's putting it in a diagonal matrix, then that's just the equivalent of having the gradient itself. So we can compute the full Jacobian in a single JVP because we know that the structure of the Jacobian is diagonal. And so you can make a clever choice of seed vectors such that you just compute that diagonal all in one go. So hopefully that makes sense. We don't have any time really to go any further, but I'm happy to chat about this over lunch with people if they're interested. This is a very simple example of something called coloring. So the idea is that in the Jacobian case, you can kind of group all of the columns together and compute them all as one. So they all have the same color. And in the idea of coloring, it's like, how do you group different columns together and compute them together in batches, like in this sort of sparse approach. So again, there's not really any time to elaborate on that too much. But there's a compressed Jacobian example where I've plucked out of thin air a clever choice of seed matrix. So the seed matrix X dot, it looks like this. So it's got 3 rows and they're just mostly zeros, but then ones in this sort of structure. And if you work through the exercise below, which again, we don't really have time, so I'll just do it now. We can type make compressed Jacobian. So this is a very similar version to what we saw before, but instead of running the JVP with the full identity matrix as the seed matrix, sorry, we've just got this reduced one. And then you can do some decompression basically to get back to what you wanted. So if we type make compressed Jacobian and then run it, then you should find that you've got the compressed Jacobian, which looks like this, and then the decompressed Jacobian, which looks like that, which is that's exactly what we had before. And basically, we've been able to compute this whole thing with just 3 JVPs, so for each of these rows. And you can see that basically all of the non-zero, well, yeah, all of the non-zero entries are in here, plus a couple of the zeros. And we can back that out in order to get to this one. So I'll leave it as an exercise to the reader to do the experiment which is mentioned, which is to do with timing. So if you increase the size of the problem, like at what point does this dense Jacobian approach start to become infeasible? And what kind of speed up do you get with the compressed approach? So this is just some plots that are comparing these different approaches from a preprint of mine from a few years ago. So the best thing you can do for certain problems is to have the analytical solution, but analytical solution here doesn't actually mean the solution of the equation we're trying to solve. It's just hand coding the Jacobian. So if you hand code the Jacobian and get it right, it's always going to be the fastest thing. But with different AD tools, or different AD approaches, you can approach that speed. So for a small problem, the matrix-free approach tends to be very good. For this particular case, the uncompressed, i.e. dense case is very, very slow. Lower is better. And then as you go to bigger problems on more numbers of processors, you start to see different patterns. So the dense approach is completely infeasible. And there's a difference between the compressed approach and then just applying matrix-free, which you can either read about further down or chat with me later. So I guess that comes to the summary, since we're out of time. We've had a brief history of AD. We've looked at the forward mode and source transformation approach, and we've tried out Tapenade for various different things, including the Taylor test. And then we've learned about this compressed approach and this matrix-free approach. And if you want to have more differentiable programming and find out a little bit about how this is going to work in practice and you could use it in your research, Then come back tomorrow and we'll look at the reverse mode and the operator overloading approach, which are sort of fundamentally different. We'll verify Tapenade works under both forward and reverse mode in a consistent way. We'll learn about computing higher order derivatives, so for example, second derivatives. And we'll try out an operator overloading tool and see some showcases of more advanced usage like solving PDE, stuff like that. And if there's time, we'll learn about checkpointing. So thanks very much for coming along, and I'm happy to chat over lunch.